another session of differential geometry class. Today we are going to discuss about geodesics. Before going to geodesics, let us have some definitions. This definition we have already seen. The vector field x along a parameterized curve alpha. Suppose alpha is given as a parameterized curve from I to R n plus 1. Then we will say that for each point t belongs to I, a vector x of t at alpha of t. That is, x of t belongs to R of alpha of t at n plus 1 for every t belongs to I. We already know that whenever you are having alpha, we are having a vector field x along a parameterized curve alpha. That means vector field we have already defined. Okay, so here what we are having is we have got an interval I, and from this to some space or surface we are defining a curve like this. So this is your alpha. So from A to B, if you are taking, this is your alpha. From here to here is your alpha. So in order to have the vector field along the curve alpha, means if you are taking every point over here t corresponds to this, we are having an alpha of t over here, right? Alpha of t. Now give the vector field to this alpha of t. Then we will say that it is a vector field x along alpha. So this vector field is x. Now a function along alpha is simply means that a function from I to R. Now examples. Let alpha from I to Rn plus 1 be a parameterized curve. Then the velocity alpha dot is a vector field along alpha. That means when you are taking alpha dot, means alpha dot of t is defined at the point alpha of t. So it is a vector field along alpha of t. D by dt of you will get alpha of t. Right? Now if you are considering modulus of alpha dot of t, that will represent the speed of alpha. So the length modulus of or a norm of alpha dot from I to R is defined from norm of alpha dot of t is equal to modulus of or norm of alpha dot of t for all t belongs to I is a function along alpha. Now this norm value is called the speed of alpha. So here we want to note one more thing as a note. Even if we are giving alpha of t1 equal to alpha of t2, does not imply that alpha dot of t1 is equal to alpha dot of t2. For example, suppose we have got a curve something like this. Some curve like this. Now at here, this is my t1 and t2, both should be the same. And suppose I am having the vectors like this. So this direction, when I am moving, this is my t1, right? So I will get the direction like this. Okay, so and coming back to this curve once more, means when I am moving like this is again become my T2, right? So T2 along this direction I will get, this is alpha dot of T1, but this is alpha dot of T2. So here, even though T1 and T2 both are the same, but alpha dot of T1 is not equal to alpha dot of T2. So this should be noted that even if alpha of T1 equal to alpha of T2 doesn't imply that alpha dot of T1 equal to alpha dot of T2. Now example, let alpha from closed interval 0 pi to R2 be defined by alpha of t equal to cos 2t sin 2t. So your alpha is defined from closed interval 0 pi to R2 and alpha of t is given as cos 2t comma sin 2t, where t belongs to interval 0 pi. What you asked to find is alpha dot. So alpha dot of t, you can easily find that alpha of t comma d by dt of alpha of t, right? Now that's equal to alpha of t comma, what is d by dt of alpha of t? This is alpha of t. So cos 2t you will get minus 2 sin 2t, and this one derivative of this you will get 2 cos 2t. So this is your alpha dot. Now suppose they are asking what is the speed of alpha. How to find speed of alpha? Suppose and speed of alpha and speed of alpha. How to find? That is norm of alpha dot of t, right? And that's equal to norm of this one, norm of alpha of t comma minus 2 sin 2t comma 2 cos 2t, right? Now this is equal to square root of, we'll get minus 2 sin 2t square plus 2 cos 2t square. Okay, so you get this as 1. The velocity vector, not 1, sorry, we'll get here what we are having is 2 square, right? That I missed. So we'll get it as root of 4 you will get. That is nothing but 2. Now this I am leaving for you to work. Find the velocity, acceleration. Acceleration means how to find acceleration? Acceleration means your alpha double dot of t, right? So that means you have first you find alpha dot of t, then again you find what is alpha dot of t dot. Okay, so this I am leaving for you as a homework to find up to this. Next, show that if alpha from I to Rn plus 1 is a parameterized curve with constant speed, then alpha dot of t is orthogonal to alpha double dot of t. So given that it's a parameterized curve with a constant speed. So constant speed means norm of alpha dot of t should be equal to c for every t belongs to I, right? It's given that is a constant. Therefore, what you are having is norm of alpha dot of t. Okay, norm of alpha dot of t equal to some constant for every t belongs to I. Therefore, norm of alpha dot of t square again should be constant, right? This also constant. Now what about alpha dot of t square? That is nothing but alpha dot of t into alpha dot of t, right? Now this equal to a constant. Now what we are having is this equal to a constant. So what is but d by dt of alpha dot of t dot alpha dot of t should be 0, right? And this equal to finding derivative alpha double dot of t into alpha dot of t plus alpha dot of t into alpha double dot of t equal to 0. That's equal to 2 times alpha double dot of t into alpha dot of t equal to 0, which implies alpha double dot of t into alpha dot of t equal to 0. That implies alpha double dot of t is orthogonal to alpha dot of t for every t, right? So this is one part. Now we can easily find if it is of constant speed, then this will hold. Okay, now given some properties, if x and y are smooth vector fields along the parameterized curve alpha from I to Rn plus 1 and f from I to R be a smooth function, then we want to verify that x plus y dot, that means the derivative, is equal to x dot plus y dot. We can see one by one. So here's the solution. Okay, before that, what is x and y? Where x plus y and fx and x dot y are defined along alpha by x plus y of t equal to x of t plus y of t. Fx of t is equal to f of t into x of t, and x dot y of t is x of t dot y of t. Okay, so the prime notation, that means when you are having dash, see this notation, this is called the prime notation. The prime notation for scalar function and dot notation for derivative of vector function that we are following. So first one, we want to find that alpha plus x plus y dot equal to x dot plus y dot. Very easy one. For that, what we have to assume is, first you assume that x of t equal to alpha of t comma x1t x2t etc xn plus 1 of t, and similarly y of t equal to alpha of t y1t y2t etc yn plus 1 of t. Now you find what is x plus y. So x plus y means again it's a vector in alpha of t with the components x1t plus y1t, x2t plus y2t etc xn plus 1t plus yn plus 1 of t. Now we want to find the derivative. So derivative of this means derivative of each term. So sum is coming, right? Because d by dt of x1t plus y1t will come. So that should be alpha of t comma dx1t by dt comma dx2t by dt. See, so this summation we can split now. Alpha of t, first thing containing everything in terms of x1, x2, x3, x4, xn plus 1. Second term alpha of t comma dy1t by dt, dy2t by dt etc dyn plus 1 of t dt. So like that we can combine. So you will get it as x dot t plus y dot t. So this result follows very easily. And the second one, fx of t is defined as f of t into x of t. So again this will become alpha of t into this f of t is a scalar one. So we want to multiply that with every vector components. That means x1t, x2t etc xn plus 1 of t. Next we want to find the derivative, right? So derivative of this. So when you are finding derivative of a single term, I am writing here f of t into x1 of t is the. So when you are finding derivative, d by dt of f of t into x1 of t, a single term only I am writing. So this should be equal to derivative of first term. So it is in scalar one. So I can put a dash, f dash of t into x1 of t plus product rule we should apply. Next term should be f of t into x1 dot of t, right? So this is a single term. Like that, n plus 1 terms will be there. So that is this thing, f dash of t into x1 t, sorry, here, plus f of t into x1 dash of t, like that. Now you combine those terms which is having f dash of t in common, right? And second bracket you write those terms which is having f of t. Okay, so you can split this into this two brackets. One is having f dash of t as common, and another one is vector part is having f of t as common. Okay, or what we are getting is this equal to finding f dash of t outside, f dash of t into, this is nothing but x of t, plus here f of t into again x of t. Third one was x dot y. So similarly x dot y we can write it as x1t into y1t plus x2t dot y2t, component wise, right? Then we find what is the derivative. Since x dot y is a scalar one, we can put here as prime. So x1t y1t plus y1 dot t x1t, x1 dot t y1t plus y1 dot t x1t. So like that we can continue for each term, and at last what you are getting is x dot t y of t, then x of t dot y dot of t. So we can have the three results or three properties. Next is the definition of geodesic. So what do you mean by a geodesic? A geodesic is an n surface, a subset of Rn plus 1, is a parametric curve alpha from I to S whose acceleration, that means alpha double dot of t everywhere, is orthogonal to S. Okay, if you're getting like that one condition, means I can put this as alpha of t. Okay, we will say that this alpha is a geodesic. I repeat, we will say a parametric curve alpha is a geodesic if its acceleration is everywhere orthogonal to the surface S. Thus, the geodesic is a curve in S which always goes straight ahead. That means if this is my surface, so every point it should be orthogonal, means my geodesic may go like this or like this, right? Only these two directions. So everywhere it should go straight ahead in the surface. Its acceleration serves only to keep it in the surface, right? Now it has no component of acceleration tangent to the surface. So it is very important, it has no component of acceleration tangent to the surface. So this is surface, means this is tangent to the surface. So no component of acceleration is tangent to the surface. Every component should be in normal direction. So here's the problem. Show that geodesic have constant speed. So geodesic, we want to say that it is having constant speed, that is alpha dot of t is some constant. That only we want to show it here. So here given that alpha is a geodesic. So alpha is a geodesic means alpha double dot of t should be orthogonal to S of alpha of t. That means alpha double dot of t belongs to S alpha of t per for every t belongs to I. That means an alpha dot of t that we know that belongs to S of alpha of t. And therefore alpha double dot of t dot alpha dot of t should be equal to 0. Now finding its derivative, d by dt of alpha dot of t square is equal to d by dt of alpha dot of t dot alpha dot of t. Now its derivative means alpha double dot of t into alpha of t plus alpha of t into alpha double dot of t, and this value we have already found by equation 1, and that value is equal to 0. So what does this means? This derivative of something is 0. That means the derivative is constant. That means alpha dot of t is a constant on I. So this implies that alpha dot t is constant. Now here is an example. Let S be an n surface containing a straight line segment. So we are having a surface over here, and this surface containing a straight line segment is given as alpha of t equal to p plus vt. That means it is having a point P passing through P and parallel to the vector V. If this is V, now this is the P plus Vt. Okay. Straight line P plus Vt. Then alpha dot of t equal to alpha of t comma V, right? Vt, with respect to t only we are derivative. So it should be V only will come to the derivative part. So this is true. Now alpha double dot of t, when you are finding, it should be 0, right? So what you are getting is alpha double dot of t is 0. So we can conclude that this alpha double dot of t is belongs to S of alpha of t per. Since any vector if you are considering in this surface, that will have dot product with this alpha double dot of t as 0. So we can say that this belongs to S alpha of t per. That means here the acceleration is everywhere orthogonal to S. Thus we can conclude that the line segment is a plane joining two points is a geodesic in the plane. As a remark, a parametric curve alpha in a vector field is geodesic in S if and only if it is acceleration alpha double dot of t is everywhere orthogonal to S. That is if and only if alpha double dot of t is a multiple of the normal, right? What was the normal? N of alpha of t for every t belongs to I. So hope you understood what is a geodesic and vector field along alpha and what is the properties. So these are the things we have discussed in today's class. I am winding up here. Thank you for your patient listening.